Esterel.
Okay, so what I want to talk about today is a calculus for a language called Esterel, which is a really interesting language with a weird semantics that I'm betting a lot of people haven't had a chance to play with before, so this should be fun. So first natural question I have is, what is this Esterel language? So Esterel is a programming language first introduced back in the 80s that has seen a lot of use in critical systems like nuclear reactor control systems or the first fly-by-wire systems on the Airbus planes. And it's seen adoption here for a lot of reasons, but the ones I'm going to talk about a lot today are its built-in facilities for non-local communication, which can be used to help coordinate and control some powerful control structures that can do things like suspend and preempt groups of threads. But it managed to do all of this while maintaining a form of deterministic concurrency. So that's a quick look at Esterel. Another question you might ask is, why do I want to build a calculus for this language? And to answer that, I want to look at a representative sample of some of the existing semantics for Esterel. So the two I'm going to look at are the constructive operational semantics and the circuit semantics. The constructive operational semantics is a reduction relation that gives an evaluator for Esterel. So it's very good at giving meaning to full Esterel programs. And the circuit semantics, in contrast, gives meaning by transforming Esterel programs into circuits. So it's very useful for compilation and optimization of Esterel programs because, as it turns out, we know how to optimize circuits very well. But what I want, and what these don't give us, is a system that is fairly easy for programmers to use and reason with, that allows for local reasoning based only on the source code of the program, and that can talk about equality between terms. So we can think about things like refactorings in the program. And to get at this, we're drawing inspiration from Plotkin's work on the lambda calculus. Just to say, I want to show you about a system that will let programmers reason algebraically about their programs. So before I can show you this system, I want to give you an intuitive notion of what a semantics for Esterel might look like. How do Esterel programs run? So Esterel belongs to a family of languages called the synchronous reactive programming languages. The reactive portion here is pretty much what you're familiar with. It just says that it's continuously responding to input from the outside as opposed to running in some sort of batch mode. The newer thing here is the synchronous part. And this comes into how Esterel responds to the outside environment. So in a traditional reactive language, you might have some message that will come in, and the program will start computing. Another message might come in, and eventually the program responds. But this setup can allow the outside world to observe things about the computation of the program, which isn't ideal. What Esterel does is instead it says that every response to something from the outside world needs to be synchronized with the incoming message. So essentially, all computation in Esterel happens in between that getting the message and sending the response, and it doesn't compute in between. You can't observe anything about that computation. And what this gives Esterel is this sort of logical notion of time, where each reaction is instantaneous and represents a tick of a clock. So you can sort of think about all the computation in Esterel as happening in 0 time. In fact, we call all these reactions instants because of this. This is kind of a vague notion, but just keep it in mind as you go forward, and we'll come back to it. So the part of Esterel, like I said, I want to focus on was its facilities for non-local communication. And the part of that I'm going to focus on is this signal form in the language, which looks like variables, but gives us a form of scoped broadcast channels in the language. And specifically, they are a form of broadcast channel that, to maintain deterministic concurrency, can only be observed to be in one state during any reaction. And specifically, they can only be observed to be either present or absent, which is to say the signal is there or it is not. And there are only two things that a program can do with a signal. It can emit the signal, which is to say make it present, or it can test for the signal's present. So the present form here says that if S is present currently, then run P. If it is absent, then run Q. So what does a program look like that sets a signal to present? So what I'm going to do is I'm going to walk through some example programs, and on the side I'm going to record what we know about the signals in the program. So this program has one local signal S, and it has two subportions of the program that are composed concurrently. The first portion is going to look at that signal S and emit some signal to the outside world based on S is present. So if S is present, then it will send O1 to the outside world. Otherwise, it will send O2. And the second portion of this program just emits S. So how can we think about running this program? Well, first we might think about trying to run this first concurrent portion. But the thing is, we don't know the value of S yet, so we can't make a choice here. So instead, let's move on and try to run the next part of the program. This part just says emit s, so we can set s to present. And now we know s's value, so we can go back to that conditional, and the conditional will take its first branch, so we'll emit O1. And now we're done, right? We've executed to the end of the program. Well, not quite. We never emitted O2, and therefore O2 becomes absent. And this is the sort of interesting thing about absence. It means that the signal isn't emitted. So how can we observe that? How can we test if a signal is absent? So this is a similar program to before. It has one local signal, but now only has one subportion that's the conditional from before. It's going to emit O1 or O2 based on S. And we want to think about how this program might run. Well, we can try to run the conditional, and we can see that nowhere in the program is S emitted. So S has not been emitted, and it cannot be emitted, so we can set S to absent. And now we know S's value, so we can take the else branch and emit O2. And once we've done that, we can say, hey, look, we've now passed the point in the program where O1 might be emitted. So it's no longer possible to emit O1, so we can set O1 to absent. So that's the high-level look at absence and presence. Let's try to put it together. And I promise this will be the most complicated program in this talk that I'm asked you to understand. This program has two local signals, S1 and S2, and it's going to have three portions composed concurrently. The first portion is going to say that if S1 is absent, then emit S2. And if S1 is present, it will do nothing. And the second program does sort of the inverse. If S2 is absent, then we'll emit S1. So what these first two portions of this program do is sort of give a complicated version of OR. It says that if one of these signals is absent, force the other one to be present. And then this third portion is going to emit S2. So how will this program run? Well, we can think about trying to run the first portion, but we don't know S1's value yet, and S1 might be emitted, so we can't do anything with this. And the same for the next portion. S2 might still be emitted, so we can't do anything with this. So now we can try to run the third portion, and we can emit S2. And now we can go back and deal with the second conditional. So we can look at this and say, OK, S2 is present. That means that we'll take the first branch and do nothing. And now, because we've taken the first branch here, it's no longer possible to emit S1. We've passed that point in the program. So we can cross that out and set S1 to absent. And now we can figure out what to do with the first conditional, which is to say we can take its else branch and emit S2. But S2 is already present, so this is just an input operation and does nothing. So that's the intuitive notion of how programs like this run. But I've kind of been a little cheeky with time here, because I told you before that we should really think about all of these reactions as happening in no time at all. But I've been giving you an order to think. So how can we reconcile this? Well, I think this is best summed up by a rather pithy quote from the creator of Esterel. Everything happens at the same time. It just happens to happen in the right order. And this intuition actually you can think of it as coming out of the circuit semantics for Esterel. When you have a circuit, it's not that one electron moves, then another electron moves, and another electron moves. The whole of physics happens all at once. But sometimes power being on a wire or not being on a wire will cause certain gates to settle to certain positions. And that's the notion we should be thinking about. We should be thinking about causality, not about ordering, not about what actual time things happen at. So how do we think about this syntactically? Well, if we look at this first program, the one we saw first, this emit statement for S can cause this conditional to make a particular choice. So I can add an arrow here that says there's a causality connection between this statement, this emit, and that conditional. And the choice this conditional makes might cause O1 to be emitted, and it might cause O2 to be emitted. And now we've overlaid a causality graph on top of the program that tells us what can cause what to happen. And the nice thing about this actually gives us a tool to reason about absence. Because if we look at this, we can go, well, S must be emitted. Nothing could stop it from being emitted. So I can cut this causal arrow because I know what's going to happen. And now I know S's value. So I know that this conditional can't take its else branch. So I can cut that causality arrow too. Now look, nothing in this program can cause O2 to be emitted. And that's why we can set it to absent. It's not in the causality graph. Now let's look at this in a slightly more complicated example. This is the third program that I showed you. In this example, the emission of O2 might cause this conditional to make a particular choice. This conditional, depending on its choice, might cause S1 to be emitted. The emission of S1 might cause this conditional to make a choice, which might cause S2 to be emitted, which might cause this conditional to make a choice. But wait a minute, that's a cycle. How can you have a cycle in causality? Well, we can use the same reasoning we used before to help break this cycle and figure out what this program means. S2 must be emitted, so I can cut this causal arrow. And I can cut the one from the other emit of S2 because it doesn't matter, emissions are idempotent. And I know that S2 is present, so I can cut the causal arrow to the else branch of that conditional. And then that conditional is not reachable, so I can cut that causal arrow too. And now, look, we've erased the cycle, and we can see that S1 will be absent. So this is how we reason about causality cycles. But there is still an issue with causality cycles here. Because if we take this program, put the causality graph back on, we can sort of think about this as we were able to deal with this causality cycle because there's an incoming edge that let us sort of deal with this oddity of the cycle. So what happens if I delete that incoming edge? What happens if I get rid of the emission of S2? Well, now we can't derive an ordering here because everything can cause everything else, so we don't know what this program means. And that's the tack what Esterel takes. It rejects programs that have these kinds of unbreakable causality cycles, and it calls them non-constructive. So that was a lot of information about causality. This is important, so I'm going to give you a brief summary. The causality graph of a program tells you what in a program can cause what else to happen. Absent means that a signal cannot be emitted. And programs with unbreakable causality cycles are rejected and called non-constructive. Or, to have a slightly more silly quote to deal with this, turns out if you want Esterel programmers, don't go to France, go to Hawaii. So, brief introduction to Esterel out of the way. What does our calculus look like? Well, we're following the sort of traditional Plotkin way of building this here. So we're going to have a set of axioms that give us a sort of core notion of what it means to run programs. We're going to take these axioms and close them over program contexts so we can sort of run anywhere. And then we're going to close that over the transitive reflexive symmetric closer to get an equality relation back out so we can reason about equality between programs. So this means we can run forward, we can run anywhere, and we can run backwards. What does reasoning with this look like? Well, if we take this first program, which is similar to the first program the first program in the talk, one possible reduction step here might be to actually run the emit. So erase the emit and then store on the side that S was emitted. And now, the next reduction step we might take is we know that S is present, so we can take a reduction step that turns the conditional into its then branch. And if we look at the program all the way on the right, that can take a similar reduction step. It can run its emit and store that on the side. And oh look, they reduced to the same program. Therefore, they must be equal. And the cool thing here is this is under program closures, so this is actually reasoning about fragments of any larger program. One other thing to point out here is that the equality relation here works within one instant. It doesn't work between instants. And you can think about this as sort of being analogous to why lambda is a value. When we're done with an instant, our program is awaiting new input, and it can't run until it gets that input. So we're done. We have some kind of value. So most of what I showed you is fairly standard. The interesting part here is going to be the axioms. But to build these axioms, I need to introduce something else to the language. Because remember, we want to reason about state here. But I also want local reasoning, so I need some kind of local state here. And to handle this, we borrow a trick from the Feldhuisen-Hebe state calculus, which is to add these row forms to the language that are going to annotate terms in the program with local state. And so we can scope the state to a part of the program and reason about it just there. And so in this case, the local state is going to be a map that's going to map signals to their statuses, which is just to say present, it was emitted, absent, it was not and cannot be emitted, or unknown, which is to say we don't know yet. Now, this calculus is rather large. There are like 20-odd axioms. I don't want to show you all of those. So I'm just going to show you the one that's relevant to absence in the way that we've been talking about it, which is how do we take a store that has some signal and make that signal absent? So this is one of the more complicated rules we have. But this says is we have some store in the program, and S is in the store, and we don't know S's value yet. Then we can set S to absent if this weird-looking condition holds. What this says is, all it says is, can S be emitted? So this can row function essentially builds that causality graph I was talking about, prunes it, and gives back all the reachable signals. If S is not in that graph, if it's not reachable, then it can't be emitted, so we can set it absent. Now this can function is actually adapted from the constructive operational semantics, and essentially what we've done here is we've adapted to work with this style of equational reasoning and with this kind of local store. So that's a quick look at the calculus, but how do we know that the calculus is good? Or rather, how do we know we actually have a calculus? And there are two questions I want to ask here. Is our calculus mathematically consistent? And does it actually describe Esterel, or does it describe some subtly different language? Now, I don't want to labor too much on the first point. All I want to say is that we have some 30,000 line aggregate proof that shows that our reduction relation is confluent. So we're pretty sure it's consistent. But I want to spend a little more time looking at the question, is this actually Esterel? Or another way of saying that, if I have some independently given evaluator, say from the constructive operational semantics, then is it true that if this calculus claims that two terms are equal, will they always run to the same value? Basically, is our calculus sound with respect to this evaluator? We would love this to be true. Unfortunately, I have a counterexample. This is the shortest counterexample we have to this. And I don't have enough time to go into detail, but basically this comes down to causality and constructivity. There are certain kinds of non-constructive programs in which our calculus does the wrong thing. You can look at the paper for more details. But like I said, in some sense, non-constructive programs are invalid. So what if we restrict this statement a little bit? What if we say that, is it sound on constructive programs? If we have two constructive programs that we say are equal, then will they always return the same thing? So to try to go about showing this, two more questions to ask. How am I going to show it's correct? And what definition of eval am I going to use? So for this first point, I don't know how to formally prove this statement yet. It's a bit tricky. So instead, I'm going to give a slightly weaker form of evidence in the form of random testing, trying to find counterexamples. And then for the evaluator, I'm actually going to pick three different evaluators. I'm going to pick the evaluator that you can get from the constructive operational semantics, the evaluator that you get from the Esterel v5 implementation of Esterel, and also the evaluator you get from hiphop.js, which is Esterel embedded into JavaScript. And the way that we've gone about doing this is we've implemented our calculus in Redux. So we now have the ability to run programs in the calculus and generate programs in the calculus. And we've written something that will convert that to Esterel v5 and run it there. It will convert it to hiphop and run it there. It will also convert it into Agda. That way we can check consistency between our Agda implementation and our Redux implementation. This was great. We found a couple of annoying bugs because of this. And we've also implemented the constructive operational semantics in Redux, and we run it there as well. So what happened when we ran this? Well, the first cool thing I find about this is we found bugs in Esterel v5 and hiphop.js. I think we found one bug in Esterel v5, which is great because it's like 15-year-old software. We found 4 or 5 bugs in hiphop, and they've all been confirmed as bugs by developers, and to my knowledge, they have all been fixed. And in the process of this acted as great debugging help for our calculus, and we did find some bugs in the calculus. And they've all been fixed, and for the last roughly 1.8 million tests, we found no counterexamples. So, wrapping up quickly, Esterel is this interesting language for safety-critical systems that need to be reactive. We've given a calculus for this language. We have shown that this calculus is mathematically consistent, and we have some evidence that it's sound using random testing. Thank you.
Okay, thank you. We have some questions on Slido, and I'll start with them. If you'd like a microphone, just raise your hand, and a volunteer will bring it to you. We are in Papal Sala 1, if that is confusing. So the question from Slido is, do all Esterel programs terminate if there's no deadlock? Is there live lock?
Yes, so all Esterel programs will terminate. And so morally, this calculus is strongly normalizing within one reduction.
All right, absent other questions from the audience, I'll do one more from Slido. Did you consider studying observational equivalence? Reduction calculi for Lambda languages are very weak compared to observational equivalence.
Yeah, so we worked a little bit with that, and we don't have a standard reduction yet. We don't have a lot of stuff we would need to think about how this works with respect to observational equivalence. So that's future work, and that falls out of this issue with constructivity that we have.
Okay, Phil, please.
It's very nice work. Where did you get the programs for your testing?
So there are two sources of programs. We ran against the standard Esterel test suite. Rather, we ran against a subset of it because we borrowed it from hiphop, and that uses a non-trivial amount of embedded JavaScript. So anything that had JavaScript in it, we didn't use. And then we also randomly generated a bunch of programs using Redx's built-in random generation facilities. And then we also have a bunch of handcrafted tests that we wrote just because we like testing our things and thinking about if they work.
And did you find any bugs in your Agda implementation?
We did find, yes, we did find a bug in the Agda implementation. Actually, the last bug we found, which was like a couple of months ago, which was there's a surprising little corner case in the Esterel semantics. Actually, one of our reviewers, when they saw that, said, actually, I think the Esterel semantics is wrong and your original choice was right. And it turns out it's that way for a very, very subtle but interesting reason. So there's more details on that in the paper.
So you went to do testing instead of approving. Do you have any idea how the actual proof might work?
Yes, it doesn't. So this issue with constructivity, sort of the way I'm thinking about proving it is we need to fix that before we could try to prove equivalence because of how deep the notion of constructivity is built into Esterel.
So the challenge is on defining constructivity.
It's on getting the calculus to respect constructivity. Constructivity is well defined. A program is constructive if and only if it reduces to a value in the constructive operational semantics. But we sort of can bypass constructivity in certain cases, and we want to fix that before we try to prove equivalence.
Any other questions? Time for one quick one in back, Max.
So you're generating these test cases, but you care more about the constructive test cases than the non-constructive programs. So how hard is it to generate only constructive programs?
So that can be done fairly easily if you really wanted to. Just generate programs that have acyclic causality graphs. We actually did generate non-constructive programs, and this is one of the weaknesses of what we're doing here is that testing framework that I showed can't disprove the original statement I gave you. So the search strategy that we built to go through the space reductions in the calculus actually respects constructiveness. So it's not a standard reduction. And so that testing process can't find the original bug. And we found that actually through the process of proving things in Agda and thinking hard about what we were doing, we realized, hey, there's a problem here.
Okay, let's thank Spencer one more time.